Okay, so this is going to be a random overview of the different images that I have as part of my research. And you can see here all the things that we're going over. And it's not really organized, but it doesn't matter. I'm just going to talk about each picture. Let's just start. We'll go through these. Let me see if we can move this over and capture that properly. Get that full there. This is showing the hottest geothermal regions. It shows you hot spots. Like if you look over here, I'm going to use my pointer here. Right here, starting in British Columbia, Vancouver, you have volcanoes all the way down here. You've got over here is the Yellowstone hotspot, and then all the way down. Right? And you have a discontinuation here around the panhandle of Alaska. Then it starts all the way out the Aleutian Islands, ringing around the Bering Sea to here, all the way down. Now this is an interesting section. And I really should open Google Earth too. While that's opening up, let's go to the next picture. This right here basically shows you the geologic ages of this is North America. So look around the Hudson Bay, which is up at the top. Oldest bedrock of North America. Here's the southwest of the U.S. I don't know how they call that. I guess it's somewhat the southwest of North America. And you got the Sea of Cortez there. Let's just flip through this. Okay, here we have a bigger picture. Let's get over here like so. Here we've got a big picture of North America, and then the red up at the top of this picture, you see this is the oldest rock, but you see there's like a ring in the southern part. The southern shore of the Hudson Bay is not part of the Canadian Shield. And basically the red here is the oldest rock. So I'm trying to understand this better, because this is a key to help us understand what the North was like many millions of years ago, hundreds of millions of years ago. Some of these are small pictures. Orogenic belts. I don't really have the depth here to talk about that right now. Here's a good picture. This is a very good picture. So maybe we can open this up full screen here. Let's get this full screen. Basically, okay, and they give you, look up at the top, they give you cross sections. Now, I don't know if this is depth. It does look like a cross section of the vertical, and the top curve looks like the surface. But in any case, what I really want to look at is down here. Okay, the whole map, and you see that there's arrows going away from the zones. On this side you've got the Atlantic. The right side of your screen, the right side, or I should go like this, the right side, you've got, it's a crack in the earth going all the way from above Iceland all the way down to where you get toward Antarctica. So this is a famous configuration that was discovered and understood. It's become understood and interpreted to a certain extent, and then they were able to extrapolate all these other theories just based on that. But I'm going to dispute that in my upcoming book, and so I'm just giving you like the basic research right now. I'm not giving you like the full scientific explanations, because that would be impossible for a video unless I was to spend like, you know, hundreds and hundreds of man hours and a scientific team. But it's easier to put this out as you know, a treatise in a book, a scientific treatise. I'm going to make a you know, it's an introductory work from a layman, but I'm going to have, you know, a board of advisors posted to show like who I'm referring to and who has made statements. So this is in the works. But why I'm disputing it is because if you look on your right side of your screen where it shows you the Atlantic, that's been used to explain everything from Pangea, supercontinent, to all these other things. But let's go to the Pacific. Look at the middle of your screen here, Pacific, and look at the west side of South America. Is also part of the Pacific. It's down there in the south, and you've got this huge like drop from the continental shelf. There's not much of a continental shelf there, relatively speaking, to the rest of, you know, the other shores of the world. You've got this severe drop, and then it just seems to roll over. So if you look at the thing there, the key down at the bottom left, they're interpreting this as oceanic subduction. So oceanic subduction goes all the way from Patagonia and then up north to Central America, and then it stops. And for most of Mexico and for most of the United States, it's not considered oceanic subduction, it's considered continental subduction. Now how do you do that? See, this is a big question. How do you go from oceanic to continental subduction and then to... That means that part of the plate, that means it would be snapping it off. If one part goes under and then along the way one part gets over, then that's going to crack at the division between the different subductions. If the subduction is under and then the subduction is the other plate under, then where they change over, that's going to split. That's going to crack the whole thing lengthwise. Or not lengthwise, widthwise. So if you consider the length of the whole subduction zone, and then it's flipping over, not flipping over, but one's under and one's over, you have to start separating there. It has to. So, I mean, I could understand it here when you transition from the Cocos plate, look there off the coast of Central America, then you're going to the Pacific plate colliding with the North American plate, and I use that term lightly, colliding. It's slow motion, if anything. You go from the Cocos plate to the Pacific plate, so I can understand where the zone changes. And they differentiated that these plates are separate. So I'm not sure what the evidence is for that, but they must be showing that separate movement. So they've got to have devices that are showing us that we're going to have to analyze the data very carefully. Now this could make it plausible. Could make it plausible. It could. Because if you notice the subduction zone further up into North America at the Juan de Fuca, which is the cause of a lot of things, they say, that plate, you switch the subduction zone to where, you know, it's like this, or it's like this. This, or this. But this is significant because if a continental continental plate is going under an oceanic plate, that's insane. That's, you know, a continent will be lost then under that plate, and also water on top of it, so that continent will completely disappear. Continental subduction is a radical idea. So where do we have proof of that? Look all around the world. Like I said, California. As a matter of fact, right near where I am. So they're trying to say that that whole part of North America is sliding under the Pacific. Now, if that's the case, look at Baja California that's split off, that's moving in a different direction. That would mean that that's just floating on top of the Pacific plate, which is an oceanic plate, and North America, the edge of North American continental plate, is just sliding underneath that. So if that's the case, that means San Diego will continue floating away as an island, and places like the Salton Sea, Death Valley, Nevada, Yuma, Arizona, all that's going to subduct and disappear, including Los Angeles, and places north of Los Angeles are going to subduct. So look, I just wanted to do a quick review, but there's so much when you look at this. There's so many like issues going on, and trying to see the bigger picture. Here we saw that one. This is showing you tectonic activity, and what do we have going on here? Also another view of the plates, and with sometimes they show differences depending on who's making okay, here's the most important thing that we really got to dwell on. This is a key, and how we interpret this to where it's going to go with other, you know, knowledge. The knowledge here of the seabed floor is significant because no seafloor in the major oceans is more than 200 or 210 million years. The oldest seafloor bed that I've been able to uncover, as far as what's available data, is in the Mediterranean. In the Aegean Sea, basically Eastern Mediterranean, around Greece, around Turkey, Cyprus, off the coast of Palestine, Middle East, and also it would touch on where the Nile empties out of Egypt. This whole area seems to be older than the 200 million mark. So this estimate as far as age is pretty old, but again, I don't totally agree with the dating methods, but I do agree it can be used for relativity, a comparison. It seems to be the oldest oceanic crust. Now, I have a time limit here. I'm on a time limit, but what I want to show you just as we're going, because I got 10 more seconds here, there's a significant feature here, up here, if you look, and it goes all the way down to fit in with this pattern here, down here. Now, if you can understand this, how these two things come together, and connect it with just north of it here, this is what I'm going to be focusing on. Okay, folks? Thanks for listening. We'll come back to this in a little while.